So let us see if we can talk about state space description of systems. It's a description that uses matrices for systems, and I know that most persons have gone through it already, but I'm going to assume that we have never seen it before. So I'm just going to proceed. Let me open up the waiting room. All right, it's one of them days when all of my devices just seem to decide, so I'm going to give no ends of problem. So let me ask one of the university students in my yard if they have what device they have. If borrow on a phone. iPhone. I need to borrow one on an iPhone. So begin that. Or a tablet.
Sir, not because of a university, that means we had money, you know. At that time, they were broke.
As the two who are here will attest. Yeah, borrowing one of them iPhone to use. Because we need to talk about space. This phone is dead. This tablet is dead, I will turn on. So I hope they don't have anything to expose on them iPhone. One go you take and one go you it. So I don't know is which one of the phones we have here.
The UV one.
The UV one out there.
They never call up the name. They never.
So I don't know. Yeah, I need to go on Zoom and I need to so that we can project what I'm talking about. This is the Zoom. Is that right? For your name? Oh. So I must take out your name?
Yeah.
Why?
For nobody research.
Sir, give me a few more seconds too.
This is a male class or male dominant class. We're not research, man.
You hear that, boss? Yeah, okay. I doubt it's working, you have money. So I don't think you have anything to fear. Four, three, eight, one. Try. Nothing to fear. So how do I join?
Right, no, yeah, you can press.
We don't know how to use these. Screen. They need passcode, Victor. What is the meeting passcode? 4 4 4 2 9 7 2. Incorrect meeting passcode. 4 4 2 9 7 2. Sorry, give me 1 second. Like somebody movie trap this class. Because not alright. 442972. So every time that is not going on. 4 4 2 9 7. Alright. That's John. 811 9033 4381 4297. I reverse this together. Yeah. Join with. Okay. All right. And me now. All right. Good evening, 1 second. Everybody hearing me? I need to pin the video named Smith. You hearing me?
Yes, sir.
Yes, sir.
All right. So, 1 second. So let us go ahead. So, we want to talk about state space. Oops. How much persons this is a new topic for?
Me, sir. Never heard that before.
Okay. So state space. Let me get my black marker. All right. So state space describes a system where we can use matrices instead of the time domain. So instead of Laplace transforms and instead of regular time domain differential equations, we can write a system of differential equations in terms of a matrix or a system of matrix. That came about in the 1980s. This way of describing a system came about in the 1980s, and it will help us to do things, some of the things, a little bit easier for some systems, especially if the system that we are going to describe is multi-input, multi-output. So our differential and difference equations can be described in terms of matrices. So the best way to go about talking about state space system is just to do a problem. First of all. So I'm going to ask us to write who is recording? let me record. I'm not the best at doing these things. All right. Those need prayers. We don't know why everything is just not working. All right. So we have this differential equation. And we are told to write it in state space form. And as one person said, never heard the term before. Well, so let me describe state our system. And let me use, you have a mass on a surface being pulled along by a force F. So, and its displacement is X. We know that F is equal to ma, so its acceleration is a. And if it's accelerating, then it's going to have a velocity v. So these three, the velocity, the acceleration, and the displacement, are what we call the state of the system, the state that the system is in. If I'm to describe this block moving on a surface field, well, as engineers, we don't really want you to tell me how pretty the block is and what color the block is and all those type of things. We use numerical data to describe. So it's moving at this velocity with this acceleration, and its displacement at time t equal whatever is 10 meters. So these three are descriptions of the state of the system, which means that if I know any of these three, if I know these three parameters, the displacement, the acceleration, and the velocity at any given time t, then I can tell you where it's going to go, how far it's going to go, where it's going to end up, if is it going to stop. I can tell you everything about the system. So the states of the system are what we use to describe, so that form equations in time, so that over time we can determine all of the things that we need to know about the block that is moving on the surface. So whenever we're talking about the system, let us say that you have a furnace. You want to know what's the temperature in the furnace. That's one thing you would want to know. And the next thing that you would probably want to know is how fast is the temperature rising, because you probably would want to be able to determine if the speed at which it is rising is too slow, then you're going to create a problem with the production. If it's rising too fast, then something got wrong with the system, and then it constitutes an emergency. So each of the systems that we have can be described by what we call state. So that is so the system has states. And whenever we're talking about space, we're talking about matrices. When we're dealing in mathematical terms. So whenever we're dealing in mathematical terms, we're dealing with matrices. So state, space, system, mean take a system, break it down, and don't describe it in a differential equation like we have here, but describe it in terms of a matrix, which is what we want to do. All right, so just to make a note of what a state is. So the state of the system is the set of variables which describe the mathematical relationship of the system. So we want to go back to this differential equation up here. And we want to say what are the states of the system. So we describe this differential equation in abstract because we're just talking about the differential equation. We don't know what the differential equation is, but we're going to assume that y, let us say for our argument, is displacement. Y can be anything, but we are going to say y is the displacement of the system. So here is what we are going to do. We are going to, by the way, I'm going to rub off all the down here. So figure one.
That is the first thing you just you
You what?
That was the only thing you wrote on the board?
Yes, Mr. Frater.
All right, I'm still on the road at Edward. I'm not reach home yet.
But not really you live. Oh, you not really you live. You're supposed to have the traffic on the road.
Chulani. All the way from town to Chulani.
You know, understand the Chilani hard to get drive around city.
You want to drive car?
But drive car, depends on where Chilani.
It's being recorded, so fret not your suitcase. You can watch it when you reach home.
All right.
But you did this already, Frater, so it's supposed to be revision.
Okay.
All right. So we are saying that this y, we're going to make it represent displacement for the purposes of our discussion. To give some, this, like I said, this differential equation can represent anything is an abstract differential equation. But we're going to let y be displacement. All right, so we're going to let y, the displacement, be the first state. So we're going to say let y be equal to x1. The next state, v, which is velocity, which is dy by dt, is going to be our second state, which we call it x2. But if you look closely, x2 is the derivative of x1. So x2 is equal to x1 dot. That means these two things are the same thing. dy by dt and x1 dot is the same thing. So we say y is equal to x1. So we're going to let the second state be equal to x1 dot. Now, the thing about it now is that this is a second order differential equation. So we usually use x1 and x2, two states to describe the system. Once the system is second order, then we're going to use two states to describe the system. The next thing that we're going to do, so let's go back over what we did. We made the first state be equal to x1, which is the displacement. We let this velocity, the derivative of displacement, be equal to x2. But we are also noting that x2 is really the derivative of x1. All right. So now we are going to make d2y by dt squared, which is the acceleration, the subject of this formula over here. So if we make d2y by dt squared the subject of the formula, then we're going to be carrying over 3 dy by dt and the 2y. So we're going to get minus 3 d2y by dt squared is equal to minus 3 dy by dt minus 2y plus u of t, ut. So we have those three things. And we are going to use, so we have one for the displacement, one state for the velocity, and then we have the acceleration here. So I'm going to rewrite this now. So I'm going to write x
One.
Oh, before that, before I write on anything else, sorry. Now, we have said that dy by dt is x2. So we're going to write down this as minus 3x2 minus 2. And we said that y is equal to x1 plus whatever the input function is. And then now this derivative that we have here, the acceleration is the derivative of the velocity. And the velocity we are calling x2. So the derivative of the velocity is the derivative of x2. So this acceleration, which is the derivative of velocity,
X2.
so we can write it as x2 dot. So now, we're going to write down three things now. So x1 dot is equal to x2 from this equation here. X1 dot is equal to x2. X2 dot, the derivative of x2 is equal to minus 3x2. Just make it a space here. A second, if it's some adjustments. All right, so we were here. X2 that is minus 3x2 minus 2x1 plus u. And we already have from up here y is equal to x1. Pregnant, we usually don't get this until we do two examples. Now, here is the set of equations. If we write it in terms of matrices, then we can write the x1 and x2 as a block. And then in the next matrix, we are going to have no x1 dot is equal to x2. So if we multiply, we know that we're multiplying row by column. So with x1 dot is equal to, you don't have any x1, so we're going to write 0 x1 is equal to x2. So we need 1 x2. So if we multiply this out, 0 times x1 is 0, 1 times x2 is x2. Here now, we have minus 3x2 minus 2x1. So we need minus 2x1 minus 3x2 and then plus now. Plus now. This u is left out. So what we do is put another column vector. We don't have any u in the first row here. So there's no u in the first row, but there's one u in the second row. So put plus 0, 1. U. And then to incorporate the y now, we say that y will be equal to 1, 0, x1, x2. So this down here is what we call the state space description of the system.
Sorry, you can go to the last line.
The last line says y is equal to x1.
Yeah, all you get in matrix is on the bottom there.
This matrix here, all right, it's just this y equal x1 that we have. So we're saying y is equal to just x1 alone. So we're writing everything in terms of the two states that we have described. So x1 and x2. So what is y equal to? Y is equal to the first state. So we just put 1, 0. So if we multiply this, is going to give me 1 times x1 is x1, and 0 times x2 is 0. So this is just, this matrix down here is capturing the y equal x1. So I am going to write the state space equation under this differential equation that we have here. And so
Sorry, can hold on, let's take off the panel. Wait, let's write a while ago, please. Just shift button board a little bit.
huh?
Shift button board a little bit so we can take off the. I think to your left or right there. So just shift.
There's is
Still
where
last
you have
part.
the 1, 1, 0, 0, 1 U.
Yeah. The 0, or get the 0, 1 u.
Oh man,
That's the
just
question.
doing the shift. No, it's alright, no, you're good now, sir.
Okay. All right. So as I was saying, what I want to do is write the, well, if you look at the tool, you can see the differential equation and you can see certain things become clearly obvious after we work a couple examples. The -3 and the -2 here and the 3, 2 here. Whatever number is here, whatever number is here, if we have a second order, you will always see it. All the other numbers are standard. The only number that you would have to determine for a second order system would be these two numbers.
I'm tired of this.
All right. So let me do a quick. So given this now, this new setup, and we are asked to write the state space. We know that we have a square matrix. We have this u vector here, which we call the input vector. And then we have y equal to the output vector. So if you're following what I was saying over here, then can you tell me what the two numbers, well, first thing, what these two numbers would be, the two top numbers here.
0, 1.
0 and 1. If you have these two numbers here,
-3, -4.
this 1, 0. This now is 2 UT, so my input vector would be
2. No. Yeah, one second.
alright, so let me just tell the names for these systems, for these things here.
Sir, remember to put the dot above the X1 and the X2.
Thank you. So here the man them in the house say, boy, them a learn. So this thing here is called the system matrix. This square matrix here. This here is called input matrix. And this here is called the output matrix. So you have a system matrix, the input matrix, and your output matrix. So we have to fill, whenever we get the differential equation for the system, then we have to fill in those. All right, so let me just digress here a little bit and say that any system that is described by a differential equation can be written as described by a differential equation or a difference equation can be written in this form. And one area in which the matrix, which we find state space system, is not only engineering, the predominant specified is engineering, but also in economics. My brethren worked on BOJ, they have one big giant matrix, 50 by 50, to describe the whole economic system in Jamaica. All of the parameters. So these X1 and X2 would represent GDP. What are the economic thing there? Gross domestic product, gross national product, export, import, how much consumers buying, how much this, that. So they're constantly updating the matrix and changing it. So one of the things that we find out, we can determine from the first thing that I would want us to know that we can determine from this thing here is the stability of the system. So how do we find the stability of the system? The stability of the system is determined by looking at the eigenvalues of the system matrix. So the stability, well, let me just write down the criteria. If the eigenvalues of the matrix have negative real parts, sorry, I left out one important word. If all the eigenvalues of the system matrix, so I left out another important word, system, of the system matrix have negative real parts, the system is stable. So if all of the eigenvalues of the system have negative real parts, then we would describe that system as stable. If they don't, then we describe that as unstable. So, and it doesn't matter what kind of system. If it's an electrical system, I know just as we said that the screen pop up and say your connection is unstable. Your internet connection is unstable. All right? So, if all the eigenvalues of the system matrix have negative real parts, then the system, whatever that system is stable. So that is why Donor BOJ, them have one person out there who spend their time looking at these things. And I should just point out to you, different people have different systems. Meaning no. Let me go digress even further from engineering. You know, like how in United States,
Jesus. Sir, go on again.
Sir, the US government don't want you to talk them business, sir.
Yeah, because it chip out a while ago.
Sir, still about
As the man say, United States, everything chip out. Nah, hear you, sir. Nah, hear a word.
sir, you might mute.
Sir, yeah, you might mute, sir.
you hear me now?
Yes, sir.
Yeah.
And we are
The computer come, this is system unstable. The computer come up and tell you say the system is unstable. Yeah, I was just digressing a little bit and saying that if you in America they have an overabundance of lawyers. In Nigeria, they have an overabundance of doctors. In Jamaica, it's two things we produce in very large quantities: teachers and nurses. No, not scammers. Only mobile alone do that. Or should only mobile people. And the Trinidad people. In France, what they produce in great abundance is engineers. So it is no, you would find that in France, the prime minister, the president of the country, and the deputy president and the parliamentarians, all of them had basic engineering training before they went on and did anything else like economics or medicine or whatever it is. Just like how in Jamaica, the teacher and nurse, them start out with teaching and nursing and then for that time was to go teachers college. So black people go teachers college and the rich people used to go through high school and they go straight to university. Black people couldn't do that. So you find a lot of teachers colleges in Jamaica. I'm saying this to say that the training that you're getting does not lend itself to you just being an electrical engineer. Don't put yourself in that box. Once you get the engineering degree, just like every Frenchman knows, you can branch off into any field that you want to branch off into that might interest you in the future. All right, so let me find, as I'm looking at a blank screen that says Tariq. I'm not seeing. Tariq, I hear you.
You're seeing your whiteboard.
You see the whiteboard?
Yes, sir.
Okay, I have seen it. So I'm going to proceed and assume that you are seeing it. I don't know why is it that I'm not seeing it. Oh, yeah, finally. Oh. All right, so let me take an example. I'm going to ask Freta. So you will help me work out this example. I'm just going to remind, this also never seen state space anywhere before. the basis of this thing here now. What's V out over V in equal to for this system that we have here?
Minus R1 over R2.
R2.
Don't all scream at me at once.
Oh, R1 over R2.
And don't tell me say system freeze. Lie.
Minus R1 over R2.
Minus R1 over R2. So let me do a quick derivation. I always like first principles when we take a first principles approach to anything that is here. You recall some things about the basic operation amplifier. It has infinite gain, infinite bandwidth, zero input impedance, infinite input impedance, zero output impedance, and all those things. But when we derive in this equation here, we call this point here, which is x. It is called a virtual earth. And virtual means just like how we have in a virtual class. It's a class, but it's not really a class. So X is Earth, but it's not really Earth. Now, just bear in mind a little thing here. This is called an inverting amplifier. So we're not going into a whole heap of the details. But whatever voltage, if I put in 5 volts here, I know that out at this other end, it's going to be something negative. If I put in a positive voltage here over here, so it's going to be negative. So if I go along a line from positive to negative, if I draw a graph, if I'm going from positive to negative, if anything in life going from positive to negative, if it's the money going from positive to negative, it must pass through zero. If you have money and then you owe money, you must have a point where you don't have no money. You must pass through zero. So this zero is the x that they're talking about, which is virtual earth. So you're going from here to here, positive to negative or negative to positive, you must pass through zero. And zero is the virtual earth. Freeze again. You hear me?
Yes, sir.
Yes, sir.
All right. So this part here is 0 volts. Now, when we're measuring 5 volts with respect to what? Is with respect to earth. You always see sometimes they draw this little earth side at the end of the 5 volts. So if on everything we measure relative to some point. So if I say this I have $1,000, I have 1,000 more than nothing. Right?
Yeah, break up.
Measure everything relative. If, for example, if my wife tells me that she has $1,000, it's not $1,000, it's $1,000 more than me. It's not $1,000 more than me. So if she doesn't have $5,000, she tells me, Mr. Woolman, you have $1,000. It's just $1,000 more than me.
Sir, close the mic with your laptop and open the mic on the phone, sir.
On the phone. Let me open this fine here. All right, do you hear me now?
Yes, sir.
Yes, sir. Much better.
It mute, but it have to go okay. Can you hear me now?
Yes, sir.
Yes, sir.
All right. So I was saying here now is that if I have something that is 5 volts, it's 5 volts above earth, above ground. You can't get the plug in the room from it now. It tell me so the battery for this will run out. I know this phone. All right. Everything I get trouble this evening. Everything. So, what's that is here? Sorry, 1 second. All right. So we have 5 volts here. We say that this 5 volts is with respect to ground. God.
Sure, we are here, man.
What? Oh. Are you seeing the video?
Yes, sir.
All right. I'm not sure why this thing not charging. Oh. Sorry, we're just checking. Find out why. Give me a second again. Still not charging. Yes, sir. Everything. I don't know what is going on. You know what one right? So tough. Not charge. Still not charged. Oh. Okay. It is charging. Yeah. All right. Are you still hearing me?
Yes, sir.
All right. So now, we are saying that this 5 volts is respect to earth. So the voltage across R2 is also the same 5 volts because this is a virtual earth. So if I say 5 volts with respect to earth, it's 5 volts with respect to earth, no matter which way the earth is. So we can safely say that whatever voltage is at the input V in is equal to R2. Is the voltage across R2. What about V out? This is respect to earth. So it's 10 volt minus 10 with respect to earth. So the voltage across R1, sorry, is the minus 10 that is here. Now, we know Ohm's law. There was an engineering student inside here now. Make sure I say, well, you a student, I walk up and down inside here. I don't want to come out, walk around and tell anybody anything.
Sir, what kind of discipline?
Can tell people that you cannot do them job.
Yeah, man, see it? We are in a session to beat him at some point. Yeah, Ohm's law. What does Ohm's law say now?
P equal IR.
V equal I. So let's call this current I 1 and this I 2. Well, we can put that V in is equal to I times R2. And let's call this V out. So the V out is equal to I2. You know, I'm going to switch these around for consistency. This is R1, this is R2. So V out is equal to
So it
and
is
let me just get
IR1. It should be IR1.
so now. So we are saying that V in is I1 times R1, V out is I2 times R2. But then there's a characteristic of operational amplifiers that says that this operational amplifier has infinite input impedance. Means that the resistance is infinite. It behaves like an open circuit. And we know that current cannot flow through an open circuit. So this I1, according to Kirchhoff's law, when it reaches right here, so it can't go through here, so because this is an open circuit. So it has to go through R2. So therefore, what we are saying is that this I1 must equal to I2. So now I1 equal I2. So we have V as equal take V out over V in. And let me just get technically correct now. The voltage here is V in minus 0. The voltage here is 0 minus V out. Zero minus. So if we divide for V,
Break up, sir.
you break up.
Yeah, you can repeat.
I think I can go back to. No, I can't.
Just repeat what you just said, sir.
No, I was saying I divide these two. So I'm going to get V in divided by V out. The i's cancel is R1 over R2. So this is V R1 over R2. So I just wanted to do that so that now I can just talk about a particular problem.
All right, so we want to.
Sir,
Yeah.
is that a resistor and a capacitor in the first branch above the up amp?
Is a capacitor and then a resistor and a capacitor.
Okay.
So we want to write down the relationship between output and input. So now this part up here, this is going to be not R but Z1, and this is going to be Z2.
So stop record.
No, the computer gone. The internet gone again. To reconnect. You see the problem too?
Yes, sir.
All right. Now, the approach to this, if you recall, the last time we spoke, we said that your capacitor is 1 over SC. Your resistance at S times. So we are going to replace each of these by its S domain. So this is 1 over S. This is 1. This is 1 over S. This is 1. This is 1 over S. So now, what is equal to? Z1. What would Z1 be equal to? Are they hearing me?
1 over S plus 1.
1 over S plus 1. What about Z2 now? Now, you have two parallel lines, and we know that for parallel is product over sum. So it's going to be product 1 over S times 1 plus 1 over S divided by sum. So it's 1 over S plus 1 over S. The product of the two lines, 1 over S is this, 1 plus 1 over S is this, and the sum is 1 over S plus 1 plus S. And we can simplify. That's 1 over S. S into S plus 1 over 2 over S plus 1 2 over S plus 1 plus S.
The diagram.
Let me do two things. Let me a different color marker.
More Jamaicans and stuff.
All right, so let me write this back over. And let me log on back to Zoom. So we're saying that Z1 is equal to 1 over S plus 1, which is equal to denominator. Now let's get this right, so just, and Z2 now is product, which is 1 over S, 1 plus 1 over S, over sum, which is 1 over S plus 1 plus 1 over S. And we're saying that that is equal to S, 1 over S times S plus 1 over S. And this now is 2 over S plus 1. So let's simplify a little further. So Z2, this is S plus 1 over S squared. This is this one of the numerator. S times just give me S squared, S plus 1. Divided by over S. Put this as over. This is the numerator is 2 plus S. So that's S plus 1 over S squared times S over S plus 2. Make it look. This cancel that. So that give me S plus 1 over S into S plus 2. So we see that? I'm talking to myself.
I hear you, sir.
So me ask if you see that.
Yes, sir.
Yeah?
Yes, sir. It's all right.
All right. So now, V out over V in is minus Z2 over Z1. So we just catch it up over here. So V out over V in is minus Z2, which is minus S plus 1 over S into S plus 2 divided by S plus 1 over S. Z2 over Z1. So that is going to be equal to minus S plus 1, S into S plus 2 times S over S plus 1. This cancel that. This cancel that. So it's going to be equal to V out over V in is minus 1 over S plus 2. Yeah, never make up a problem out of your head. Because we have a problem. Throw more water in there. All right. So now, so V out over V in. So we're going to multiply across. Care about this. Up top here.
Yes, sir.
So V out over V in is minus 1 over S plus 2. We're going to cross multiply. So this is S plus 2. V out is equal to minus V in. Now what we said that the S represented again? What we said the S represented?
The state.
No, we don't restate it. We're going back from lectures past. S.
Laplace.
Laplace.
Yes, so Laplace. So when we have S, what it represents S squared, what it represents S cubed, but what Laplace? I'll give you the topic, you know, what the S represents. You what? Mm-hmm.
Frequency domain.
No. I forgot to have some revision. Remember we tell you that S represented the first derivative.
And that's your tax.
Yes, and that matter. So this now would be d s would be dv out dt plus 2 v out is equal to the minus v in. So that is the differential equation. Representing the system. Unfortunately for us, we can't, fortunately, whichever one. We only talk about state space with second order system. So now that we have derived, may I hear you? Let me join the computer audio with this again. Where was that, Frito? Take off this one for me. Yes, where is it now, Frito? Mr. Frito?
Nothing Frida there. Nothing Frida there, sir.
In Ghana again?
Never there. I'm still live on the road.
All right.
I'm gonna get disconnected or
I know you have to go. Talk again, Frito. All right. Hush, Frito, I'm going to deal with you like with the battlefield. And you're wounded and the enemy is firing fear shot. I've left you behind here. All right. So now. So let me just make up note. System is first order. No state space. But I'm going to add something to this system here now. I'm going to go back through the process again. We know here is 1 over s plus 2. What about here now? What would that be equal to? We wanted to work out the transfer function and the relationship between input and output. This is the one. Yeah?
This is still not cascade.
You're saying, sorry, you're saying that because the system, previous system was a first order, there's no, you can't represent it as a state or space?
State space. You can't write it as a matrix because you can't, well, remember, a second order system is a 2 by 2 matrix. This is a first order system. One derivative, so we can write it as a matrix. We can have a 1 by 1 matrix.
Oh, okay.
All right. So mirror about this, and let's go again. So we know that this system is 1 over s plus 2. But what about this now? It's not an operational amplifier. So there's a voltage across here, which is 1 over 2s plus 1. That's the total. And we want the voltage across 1 over 2s. So the V out over V in is equal to 1 over 2s over 1 plus 1 over 2s. And we can simplify that. One over 2s divided by this is 2s plus 1. So I cancel. That gives me 1 over 2s plus 1. So our V out over V in is 2 cascading system. So we just can write V out over V in is equal to minus 1 over s plus 2. That's for the first system. Times 1 over 2s plus 1. That's for the second system. So V out over V in would be equal to negative 1 over 2s squared plus 3s plus 2. And if we're going to write that, so now tell me, what that is equal to as a differential equation. The s squared will represent what?
Second derivative.
Second derivative. So we write that as 2 dv out dt squared plus 3 dv out over dt plus 2v out is equal to minus v in. To write it in as a matrix, we would have to divide everybody by 2. We do have a constant here. So we write 2 dv out dt squared plus 3 over 2 dv out dt plus 2 divided by 2 is 1 is equal to negative 1/2 v in. So now this we can write in state space form. All right. So somebody can return back over here. It's all right.
Yes, sir.
All right. So somebody can tell me what this would be in state space form now. We have x1 dot x2 dot is equal to a matrix plus the input matrix. The input is not u but v, and the output is not y but v out.
You have X over Y, X and Y, plus V.
Alright, so tell me what I put in here now.
Alright, 0, 1,
1,
0, 1.
1, negative.
minus 1, and minus 3 over 2.
What goes here?
1.
No.
No.
Half.
A half, sir. Negative a half.
So this would be our state space description. Now, suppose I want to find out if this system is stable. Then I need to find the eigenvalues of this matrix here. So now, let's determine the stability of this.
Hold on 1 second. Sir.
Okay.
Alright, check out later.
All right. How do we find the stability, the eigenvalues for our system?
Lambda I minus A.
Lambda A. No,
Equals 0.
Equals 0, yeah. Lambda A.
And our A in this case would be 0, 1, negative 1, negative 3 over 2. So we're finding the determinant of that. So that's going to be, take everything in one. Lambda minus 0 is lambda. 0 minus 1 is minus 1. 0 plus 1. And lambda plus 3 over 2. So that's lambda. This times this is lambda plus 3 over 2 minus 1 times minus 1. The product of these two, the difference, supposed to be equal to 0. This time this minus this time this equals 0. So lambda squared plus 3 over 2 lambda plus 1 equals 0. So 2 lambda squared plus 3 lambda plus 2 equals 0. So, man with the MATLAB, tell me what lambda is equal to. So on the MATLAB, put in 2, 3, 2 on the rows, and then tell me what is this equal to.
Sir, minus 0.75 plus or minus 0.6614 I.
So for it to be stable, this part has to be negative. So since it is negative, system is stable. So it's stable because the front part of the root is negative. All right. So we're going to do one more example.